Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 2 of the course on econometric methods for statisticians, data scientists and engineers. The title of this lecture is Matrix Methods in Econometrics. The first question arises, why we need different metric methods in econometrics. Actually, different models which we use in econometrics involve the relationships between a number of variables. Some of the models which have just one equation, one dependent variable and a number of independent variables, and in some other models we have more than one equations. So, basically all these models are multivariate in character. Our problem is to apply different statistical procedures to these models. Now, if we use the different matrix tools, different matrix methods for analyzing these models, then our life becomes simpler. Simpler in the sense that we can easily derive different estimators, we can develop different procedures for testing the hypothesis, etc. if we use the matrix notations and matrix procedures. So, that is why these matrix methods form a foundation or basis of the econometrics. So, in this lecture I am going to cover some of the basic results of matrix methods which we are going to use in subsequent lectures, which are essential for the subsequent lectures. Of course, I am not going to give the detailed derivations of all the results. Of course, I will give you the derivations of few results. If you are interested in the derivations of other results which I am going to skip here in this lecture, then you may consult some good matrix algebra book. Now, first we define vector. A vector is an ordered sequence of elements arranged in a row or column. We have a set of elements, say A1, A2, An, and suppose we arrange these elements in a column like this. So, this kind of arrangement of elements is called a vector. This A is a vector. This A is actually a column vector because we have arranged the elements in a column, and the order of this vector is n cross 1. The ith element of this vector is Ai. Similarly, if we arrange these elements in a row, then we get a row vector. Then we define the transpose of a vector A as, say, A transpose equal to, you arrange all these elements in a row. So, A transpose is a row vector. So, actually the order of this vector is 1 cross n. This has one row and n columns, you can say. Now, suppose B is another vector which has elements B1, B2, Bn. So, B is also n cross 1 vector. Then we define A transpose B equal to summation j equal to 1 to n Aj Bj. So, how we get A transpose B? A transpose is equal to A1, A2, An, this row vector, and B is B1, B2, Bn. So, we multiply A1 by B1 plus we multiply A2, the second element of A, by the second element of B, B2, and so on, plus A and Bn. So, you get summation j equal to 1 to n Aj Bj. Then the Euclidean distance between two vectors. Say, suppose you have two vectors x and y. Both of these vectors have n elements. So, x is of order n cross 1, y is of order n cross 1, and dxy denotes the Euclidean distance between x and y. So, the Euclidean distance is defined as, say, dxy square is equal to summation j equal to 1 to n xj minus yj square. So, basically what we do? We take the difference between the jth element of x and jth element of y. So, you get xj minus yj, we take a square of this and then we take summation j equal to 1 to n. And you can easily verify that this summation is equal to x minus y transpose x minus y. In vector notations, you can write the Euclidean distance or the square of Euclidean distance as x minus y transpose x minus y, or dxy is equal to x minus y transpose x minus y to the power half. Then we defined linearly dependent and linearly independent set of vectors. So, suppose you have a set of vectors a1, a2, ak. So, we have k vectors a1, a2, ak. These vectors are said to be linearly dependent if there exists k constants c1, c2, ck, which are not all equal to 0, means at least two of these constants are not 0, such that c1 a1 plus c2 a2 plus so on plus ck ak is equal to 0. It is possible for you to form a linear combination of a1 a2 ak which has value 0. Actually, c1 a1 plus c2 a2 so on plus ck ak is a linear combination of vectors a1 a2 ak. Further, a1 a2 ak are linearly independent if c1 a1 plus c2 a2 plus so on plus ck ak equal to 0 implies that all the constants c1, c2 so on ck are equal to 0. So, for linearly independent vectors a1, a2, ak, it is not possible for you to obtain such kind of linear combinations c1 a1 plus c2 a2 plus so on plus ck ak of the vectors a1, a2, ak with these coefficients or constants c1, c2, ck not equal to 0. If the vectors are linearly dependent, then this equality implies that all the constants c1, c2, ck are equal to 0. Orthogonal vectors. Now, suppose you have two vectors a and b, both are of same order, say both are of order n cross 1, and then a transpose b is equal to 0. A transpose b means summation j equal to 1 to n aj bj, and this summation is equal to 0. Then we say that the vectors a and b are orthogonal vectors. A and b are orthogonal to each other. Further, suppose you have a set of m vectors a1, a2, am. Then this set of m vectors is said to be mutually orthogonal if every pair of vectors is orthogonal to each other. That is, for all I not equal to j, ai transpose aj is equal to 0. Say a1 transpose a2 is equal to 0, a1 transpose a3 is equal to 0, and so on, a1 transpose am is equal to 0, and so on. So, for all I not equal to j, ai transpose aj is equal to 0. Then we define orthonormal vectors. So, a1, a2, am are mutually orthonormal if ai transpose aj is equal to 1 if I is equal to j, and 0 if I is not equal to j. So, the vectors a1, a2, am are mutually orthogonal to each other, and ai transpose ai is equal to 1 for all I. So, in fact, length of each vector is equal to 1. So, we write it ai transpose aj equal to delta ij. Delta ij is called the Kronecker delta. So, delta ij is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. Now, we define a matrix. Actually, a matrix is a rectangular array of numbers. So, suppose you have m n numbers A11, A12, so on A1n, A21, A22, so on A2n, and so on AM1, AM2, so on AMN. We arrange these numbers into say m rows and n columns. So, the first column has numbers A11, A21, so on AM1 and so on. The last column has numbers A1n and so on AMN. So, A is called a matrix of order m cross n and its ijth element is Aij. It means whenever we write a matrix of order 4 cross 3, the matrix has 4 rows and 3 columns. Then we define a transpose of a matrix A. We denote it by A dash. So, A dash is the notation which we are going to use for transpose of a matrix in subsequent lectures. To obtain the transpose of a matrix, we simply arrange different rows of A as different columns. So, the first row of A is the first column of A transpose and so on. The last row of A is the last column of A transpose. So, in fact, A transpose is a matrix of order n cross m. So, if A is a matrix of order m cross n, then A transpose is a matrix of order n cross m. Obviously, the ijth element of A is the jith element of A transpose. Further, if m is equal to n, means number of rows is equal to number of columns, then A is called a square matrix. So, for a square matrix, number of rows is equal to the number of columns. Now, we define symmetric matrix. Suppose A is a square matrix. We define symmetric matrix just for square matrices. So, for the square matrix A, it is called a symmetric matrix if A transpose is equal to A. So, a square matrix is symmetric if its transpose is equal to the same matrix. So, obviously, for the symmetric matrix, Aij is equal to Aj for all I and j. If you have two matrices A and B of the same dimension, then they can be added or subtracted. So, suppose A is of order m cross n with ijth element Aij, B is of order m cross n with ijth element Bij, then for obtaining A plus B, we simply add the elements of A and B. Means we add the ijth element of A with the ijth element of B to obtain the ijth element of A plus B. Or to obtain the ijth element of A minus B, we simply take Aij minus Bij. Obviously, A plus B is equal to B plus A, because Aij plus Bij is equal to Bij plus Aij. And if we take transpose of A plus B, then A plus B transpose is equal to A transpose plus B transpose. Now, we define matrix product. So, suppose A is m cross n matrix with ijth element Aij. So, for A, number of rows is m, number of columns is n. P is a matrix of order n cross q. So, for B, number of rows is n. So, number of columns of A is equal to number of rows of B. So, actually you can define the product of two matrices A and B, say AB, if and only if the number of columns of A is equal to the number of rows of B. Then we define AB equal to, say, C, the ith element of C is CIL, the order of C is m cross q, means C has m rows, the number of rows of C is equal to the number of rows of A, and number of columns of C is q, which is equal to the number of columns of B, and CIL is equal to summation j equal to 1 to n Aij Bjl. So, suppose Ai transpose is the ith row of A and Bl is the lth column of B. Then to obtain CIL, what we do? We simply take AI transpose BL. Now, in general, AB is not equal to BA. So, we take this example, A is of order 2 cross 3, B is of order 3 cross 2. So, you can define AB as well as BA. AB is of order 2 cross 2 and BA is of order 3 cross 3. To obtain AB, we simply multiply, say suppose you have to obtain the first element of AB. So, we simply multiply the first row of A and the first column of B. So, 1 into 2 plus 2 into 5 plus 3 into 1 and ultimately you get 15. To obtain the 1/2th element, we take the first row of A and second column of B. So, 1 into 1 plus 2 into 4 plus 3 into 3. So, you get 19 and so on. So, this is how you get AB. Similarly, you can obtain BA and then you can easily verify that AB is not equal to BA. Of course, for this example, you can define both the products AB as well as BA, but AB is not equal to BA. Now, you define vector space. A vector space is the set of all possible vectors that can be obtained as a linear combinations of the vectors A1, A2, Ak. So, suppose you have a set of k vectors A1, A2, Ak. You take a linear combination of the form C1 A1 plus C2 A2 plus Ck Ak. You take all possible linear such kind of linear combinations. So, for corresponding to each linear combination you get a particular vector, and if you take all possible linear combinations, such linear combinations, then you can get a set of vectors, and that set of vectors is called the vector space spanned by the vectors A1, A2, Ak. So, the set of all possible vectors that can be obtained as a linear combinations of vectors A1, A2, Ak form a vector space spanned by the vectors A1, A2, Ak. And the minimal number of vectors needed to span a vector space is called the dimension of that space. The dimension of a vector space is the minimal number of vectors needed to span that particular vector space. Now, suppose you have a matrix A, then the space spanned by the columns of matrix A is called the column space of A, and the space spanned by the rows of matrix A is called the row space of matrix A. Then the dimension of the column space is called the column rank of A. Similarly, you may define the row rank of A, which is the dimension of the row space of A. Now, suppose you have an m cross n matrix which has column rank R, then obviously R is less than or equal to n, and if R is equal to n, then we say that A is of full column rank. Column rank is equal to the number of columns. In fact, the row rank of a matrix is always equal to its column rank. So, row rank of A is equal to column rank of A, and this is called the rank of matrix A. Again, I am not going to give you the proof of this result. Then we define minor of a matrix as, say, minor of a matrix A is the determinant of some smaller square matrix obtained by removing one or more of rows and columns of A. So, if we remove some of the rows of A or some of the columns of A, and then we ultimately obtain a square submatrix of A, then determinant of that submatrix is called the minor of matrix A. The matrix A is of rank R. Then you can obtain at least one R cross R minor of matrix A, which is different from 0, which is not equal to 0. and every r plus 1 cross r plus 1 minor of A is 0. So, one can also use this procedure for obtaining the rank of a matrix A. You take all possible minors of A and then you try to obtain the value of R, which is the value for which at least one minor is not equal to 0, and all the minors of higher order are 0. Then R is the rank of that matrix. Then we define non-singular matrix. Suppose A is a square matrix of order n cross n, and rank of A is n, means A is of full row rank as well as full column rank. And since rank of A is equal to n, then determinant of A is not equal to 0. The only possible minor of A of order n is determinant of A, and since rank of A is n, so this is not equal to 0. Then we say that A is a non-singular matrix. Now, suppose A is m cross n matrix of rank n, then rank of A transpose. What is the order of n A transpose A? This is of order n cross n, and rank of A transpose A is also n. So, A transpose A is a non-singular matrix, provided the rank of A is equal to the number of columns of A. Again, rank of matrix A is equal to rank of A transpose A, and this is equal to rank of A transpose. So, all the three matrices A transpose A and A transpose have the same rank. Then if A is of order m cross n, B is of order n cross q, then transpose of A is equal to A itself. A transpose is equal to A, and A B transpose is equal to B transpose A transpose. So, to obtain A B transpose, you simply take B transpose first, and then you take A transpose, and then you multiply B transpose A transpose. Now, we define diagonal matrix. D is a diagonal matrix if all its elements are equal to 0 except the diagonal elements. Means, if say Dij is the ijth element of D, then Dij is equal to say Di for I equal to j and 0 otherwise. So, all the diagonal elements are non-zero and off diagonal elements are equal to 0. We can also write D as diagonal D1, D2, Dn. So, D is a diagonal matrix, and if in the diagonal you have elements 1, 1, 1, so on, then this matrix is called an identity matrix, and we denote it by In. In is an identity matrix of order n. So, this is of order n cross n. Again, for any matrix A of order m cross n, A(in) is equal to A itself. So, if you multiply A by In, then you get the matrix A itself. Then we define inverse of a matrix for a square non-singular matrix A. Inverse of A, we denote it by A inverse, is a matrix such that A inverse A is equal to A inverse equal to In. If we pre-multiply A by A inverse or post-multiply A by A inverse, then you get the identity matrix. Of course, you can define inverse of a matrix only for square non-singular matrices. Again, for a non-singular matrix A, if you take inverse of A inverse, then A inverse is equal to A itself, and if you take inverse of A transpose, then inverse of A transpose is equal to A inverse transpose. Again, if A and B are two non-singular matrices of order n cross n, so both A and B are non-singular square matrices and both are of same order, then A B inverse is equal to B inverse A inverse. You can easily verify this result. You simply multiply A B by B inverse A inverse, and B inverse is equal to identity matrix. So, you get A inverse, again A inverse is equal to identity matrix. So, A B inverse is equal to B inverse A inverse. Then for the diagonal matrix D, D inverse is equal to diagonal D 1 inverse, D 2 inverse, so on D n inverse. Again you can easily verify this result. You simply multiply, take D inverse D. D inverse D is equal to identity matrix. Now we define eigenvalues and eigenvectors. Suppose A is a square matrix of order n cross n, then you take f lambda equal to determinant of A minus lambda I n. Now this is actually a polynomial of order n in lambda. If you take determinant of A minus lambda I n, then this is a polynomial of order n in lambda. And if you take the characteristic equation, this equation is called the characteristic equation. Determinant of A minus lambda I n is equal to 0. Then since this is a polynomial of order n in lambda, you get n roots of this characteristic equation. Say lambda I equal to 1 to n. These are the n roots of the characteristic equation. Then lambda i's are called eigenvalues, characteristic roots or latent roots of A. Now, since for each lambda I, determinant of A minus lambda I n is equal to 0. So, A minus lambda I n is a singular matrix. This has determinant 0. And since this is a singular matrix, you can find a vector Q I such that A minus lambda I n Q I is equal to 0. Say different columns of a singular matrix are linearly dependent. So, you can find a linear combination of different columns of A minus lambda I n which is equal to 0, or A Q I is equal to lambda I Q I. Then Q I for I equal to 1 to n, these are called the eigenvectors of A, or actually Q I is the eigenvector of A corresponding to the eigenvalue lambda I. Now, we define idempotent matrix. Suppose A is a square matrix such that A square is defined as A into A. A into A is equal to A. Then A is called an idempotent matrix. Then if A is an m cross n matrix of rank n, then if we define P equal to A transpose A inverse A transpose, then P is an idempotent matrix. Or if we define M equal to I m minus A transpose A inverse A transpose, then M is also an idempotent matrix. So, you can easily obtain P square equal to A transpose A inverse A transpose, then we again take P, then A transpose A is equal to A transpose A into A transpose A inverse is equal to identity matrix. So, you get A transpose A inverse A transpose, and this is equal to P. Similarly, you can verify that M square is equal to M. So, M is also an idempotent matrix. Further, you can easily verify that M A is equal to 0 because M A is equal to I m minus A transpose A inverse A transpose, and then we multiply it by A. So, you get A minus, you get A transpose A here. So, A transpose A inverse A transpose A is identity matrix. So, finally, you obtain A minus A which is equal to 0. Similarly, you can obtain A transpose M also equal to 0. Now, suppose we define a matrix P equal to 1 upon n ln transpose, where ln is a n cross 1 vector with all elements equal to 1. So, ln is this vector, and then we define Q equal to I n minus 1 upon n ln transpose. So, obviously, Q is equal to I n minus P. Then you can observe that P y is equal to 1 upon n ln transpose y. Now, ln transpose y is equal to summation j equal to 1 to n y j, because all the elements of ln are 1. So, Ln transpose y gives you the sum of all the elements of y. Then 1 upon n Ln transpose y will give you y bar, and then if you multiply y bar by Ln, then you get a vector with all elements y bar so on y bar. So, P y gives you y bar into Ln. Then Ln transpose is a matrix with all elements equal to 1. This is a n cross n matrix and it has all elements equal to 1. Further, if you define Qy is equal to I n minus p. So, Qy is equal to y minus p y, or you get y minus p y is equal to y bar Ln. So, basically if you pre-multiply vector y by q, it gives you the deviations from mean. Each element of y minus y bar Ln is deviation from mean, means the ith element of y minus y bar Ln is y I minus y bar. Further, you can easily verify that P and Q are idempotent symmetric matrices. If you take the square of P, then this is equal to 1 upon n square Ln transpose Ln transpose. Then Ln transpose Ln is equal to n. So, you get 1 upon n square into n Ln transpose, or 1 upon n Ln transpose, which is equal to P. So, P square is equal to P. Similarly, you can verify that Q square is equal to Q and PQ is equal to 0. This also you can easily verify. Now, we define orthogonal matrices. So, a matrix A, which is of order n cross n, so A is a square matrix, is said to be orthogonal matrix if A transpose A is equal to I n, and this is equal to A transpose. And here are some properties of the orthogonal matrices. So, A transpose is equal to A inverse. Obviously, A transpose A is equal to I n, and then A transpose gives you the inverse of matrix A. Determinant of A is equal to plus 1 or minus 1. Then, if A I is the ith column of A, then A I transpose A j is equal to delta I j, which is canonical delta, where delta I j is equal to 1 if I is equal to j, and it is 0 if I is not equal to j. And if A I is the ith row of A, then A I A j transpose is equal to delta I j. And if A and B are orthogonal matrices, then A B is also an orthogonal matrix. To prove this second result, we simply take the determinant of A transpose A, which is equal to I n. So, determinant of A transpose A is equal to 1, and this is equal to determinant of A transpose into determinant of A. Then determinant of A transpose is equal to determinant of A. So, you get determinant of A square. So, obviously, determinant of A is either plus 1 or minus 1. Then A is an orthogonal matrix. Ijth element of A transpose A is A I transpose A j. A I transpose A j will give you the ijth element of A transpose A. So, obviously, A I transpose A j is equal to 1 if I is equal to j and 0 if I is not equal to j. Similarly, you can show this result also for the rows of A. and then if A and B are orthogonal, then A B is also orthogonal, because A B transpose A B is equal to B transpose A transpose A B, and then A transpose A is equal to identity matrix. So, you get B transpose B, again B is also orthogonal matrix. So, this is also identity matrix. So, this shows that A B is also an orthogonal matrix. Now, suppose A and B are two square matrices of order n cross n, then these two matrices are said to be similar if there exists a non-singular matrix Q such that B is equal to Q inverse A Q. So, if you can write B as Q inverse A Q, then B is similar to A. Then you can easily verify that A is similar to A, because you can always write A equal to I n inverse, which is I n A I n. Then if A is similar to B, then B is similar to A, because you can write A as Q B Q inverse, or Q inverse B Q inverse. So, B is also similar to A, and you can easily verify that if A is similar to B and B is similar to C, then A is similar to C. So, if you can write B as Q inverse A Q, and you can write C as say P inverse B P, then C can be written as P inverse, you can write B as Q inverse A Q P, which is equal to Q P inverse A Q P. So, A is similar to B, because Q P is a non-singular matrix. Now, suppose A is a non-singular matrix, then A is similar to a diagonal matrix, that is, there exists a non-singular matrix Q such that Q inverse A Q is equal to lambda, which is equal to diagonal lambda 1, lambda 2, lambda n. In fact, these lambda 1, lambda 2, lambda n are the eigenvalues of A, or you can write A equal to Q lambda Q inverse. Well, I am not going to prove this result. Then the next result is, suppose A is a square matrix, then there exists an orthogonal matrix Q such that Q transpose A Q is equal to lambda, or A is equal to Q lambda Q transpose. To prove this result, suppose Q 1, Q 2, Q n are n linearly independent eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, lambda n respectively. So, Q I transpose Q I is equal to 1. Then we can write Q equal to Q 1, Q 2, Q n, means the columns of Q are the eigenvectors Q 1, Q 2, Q n. Then obviously, Q transpose Q, it has ijth element, Q I transpose Q j, which is equal to 1 if I is equal to j and 0 if I is not equal to j. Now, A Q is equal to A Q 1, A Q 2, so on A Q n. Now, A q 1 is equal to lambda 1 q 1, A q 2 is lambda 2 q 2, so on lambda n q n, and then you can write it as q 1 q 2 q n, and the diagonal matrix with diagonal elements lambda 1, lambda 2, lambda n, or q lambda. Then q transpose A q is equal to q transpose q lambda, which is equal to lambda. So, you get this result. Now, suppose A is n cross n idempotent matrix and rank of A is equal to R is less than or equal to n. Then the eigenvalues of A are 1 or 0. Trace of A is equal to rank of A equal to R. If P is orthogonal, then P A P transpose is also idempotent matrix. I minus A is also idempotent matrix, and A I minus A is equal to 0 and I minus A is also equal to 0. To prove the first result, say the eigenvalues of A are either 0 or 1, there exists an orthogonal matrix Q such that A is equal to Q lambda Q transpose. Then A is an idempotent matrix. So, A square is equal to A. So, A square is equal to Q lambda Q transpose Q lambda Q transpose. Then Q transpose Q is identity matrix. So, this is equal to Q lambda square Q transpose. So, you get the result Q lambda Q transpose equal to Q lambda square Q transpose, and this implies that lambda I is equal to lambda I square for all I. Lambda I equal to lambda I square implies that lambda I is either equal to 0, because 0 square is equal to 0, or it is equal to 1. Then you also know that if rank of A is equal to R, then R eigenvalues of A are non-zero and n minus R eigenvalues are equal to 0, and those R non-zero eigenvalues are 1. So, if you take trace of A, then trace of A is also equal to R, because trace of A is equal to the sum of all the eigenvalues, and out of these n eigenvalues R are equal to 1 and remaining n minus R are equal to 0. So, you get trace of A equal to rank of A equal to R. Then if P is orthogonal, then P A P transpose is also idempotent, because if you take P A P transpose square, it is equal to P A P transpose P A P transpose. Then P transpose P identity matrix. So, you get P A square P transpose, which is equal to P A P transpose, because A square is equal to A. Again, I minus A is also idempotent. You just take square of I minus A, you get I minus A plus A square, then A square is equal to A. So, ultimately you get I minus A. So, you can easily verify it. Further, A into I minus A is equal to A minus A square, then again A square is equal to A. So, you get A minus A, which is 0. Similarly, I minus A into A is also equal to 0. Then if A is a square symmetric matrix, then you can write A equal to u lambda u transpose equal to summation I equal to 1 to n lambda I u I transpose, where lambda is equal to the diagonal matrix lambda 1, lambda 2, lambda n with diagonal elements as the eigenvalues of A, and u is equal to u 1, u 2, u n. This is the matrix of standardized eigenvectors, that is u transpose is equal to u transpose u equal to I n. So, this result you can easily verify by using the previous result, this theorem. Then determinant of A is equal to product I equal to 1 to n lambda I, because determinant of A is equal to determinant of u, determinant of lambda, determinant of u transpose. Then determinant of u is 1, determinant of u transpose is 1, and determinant of lambda is equal to product of lambda 1, lambda 2, lambda n. So, you get determinant of A equal to product I equal to 1 to n lambda I. Similarly, trace of A is equal to summation I equal to 1 to n lambda I, because trace of A is equal to trace of u lambda u transpose, which is equal to trace of lambda u transpose u transpose u is I n. So, trace of lambda you get, and trace of lambda is summation lambda I. Then A to the power m is equal to u lambda to the power m u transpose. This also you can easily verify. Now, we define partition matrices and some results for the partition matrices. So, the presentation of a matrix by the congruity of two or more matrices, say suppose M is n cross n matrix, and we write M as A, B, C, D, where A has say p rows, p columns. So, obviously, B has n minus p columns, and here also we have n minus p rows. So, A is of order p cross p, B is of order p cross n minus p, C is of order n minus p cross p, and D is of order n minus p cross n minus p. So, we write M as A, B, C, D, and then we obtain the inverse of this partition matrix in terms of the inverse of matrices A, B, C, D. So, suppose the inverse of this partition matrix M is M inverse equal to E, F, G, H, then M inverse is the identity matrix, and this is equal to, we just partition this identity matrix as say I p 0 0 I n minus p. So, p rows p columns and n minus p rows n minus p columns. Then we multiply M by M inverse. So, we obtain A e plus B g equal to I p. We simply multiply this matrix by M inverse. So, we get A into E plus B into G equal to I p. Then we get A into F plus B into H. This will give you 0, A f plus B h equal to 0. Similarly, you get C e plus D g equal to 0 and C f plus D h equal to I n minus p. And basically, your objective is to obtain the values of E, F, G, H. So, from this equation 3, you obtain G equal to minus D inverse C e from here. Remember, D is a square non-singular matrix. So, you can take inverse of D. And then from 5 and 1, we substitute the value of G in 1 from equation 5. So, we obtain A e, and then we substitute G equal to minus B D inverse C e, and from here you can obtain the value of E. E is equal to A minus B D inverse C whole inverse. because this is equal to I p. So, you get the value of E from here, and if we substitute the value of E here, then we get the value of G. So, you get this value of G. Again from equation 4, H is equal to D inverse minus D inverse C f, and then we substitute the value of H in equation 2 from equation 7. So, you get f equal to minus A minus B D inverse C whole inverse B D inverse. So, you get the value of f here, and then we substitute the value of f in this expression. So, you get H equal to D inverse plus D inverse C A minus B D inverse C whole inverse B D inverse. So, you get these values of E, F, G, H, and from these values you can get the value of M inverse. You replace E by this matrix, F is equal to this, G is equal to this, and H is equal to this. Here we assume that D is a non-singular matrix. Another alternative derivation of this result is, suppose A is non-singular. So, means you can apply this method for the case when D is non-singular also. Just you have to slightly modify the derivation. So, if A is non-singular, then we pre-multiply A, B, C, D by this matrix I 0 minus C A inverse I, and post multiply by I minus A inverse B 0 I, and then we obtain the matrix 0 A 0 0 D minus C A inverse B. Again, you can easily verify that if you take inverse of this matrix, then you get this matrix. In fact, if you multiply these two matrices, then you get the identity matrix. So, the inverse of this matrix is this matrix. So, from here we obtain M equal to A, B, C, D equal to, you take this matrix towards this side. So, you have I 0 C A inverse I, you take inverse of this matrix, then in between you have this matrix, and then you take inverse of this matrix, which is equal to I A inverse B 0 I. Now, from here we obtain determinant of M equal to, determinant of this first matrix is 1, because in the diagonal you have all the elements equal to 1, and in the matrix is actually a triangular matrix. All the elements towards this side are 0. So, the determinant value of this matrix is the product of diagonal elements. So, determinant of this matrix is 1. Then determinant of this matrix is determinant of A into determinant of D minus C A inverse B, and again determinant of this matrix is 1. So, you get determinant of M equal to determinant of A into determinant of D minus C A inverse B. So, you get this result also. Further, A, B, C, D inverse is equal to, you simply multiply these three matrices, you take to obtain A, B, C, D inverse, you simply take inverse of this matrix, you take inverse of this whole matrix equal to inverse of this. Then inverse of this whole matrix is inverse of this into inverse of A, B, C, D into inverse of this, and then you can easily obtain the inverse of this matrix, which is equal to A inverse here, 0 here, 0 here, and D minus C A inverse B whole inverse here, and then you can solve it. So, finally, you obtain A, B, C, D inverse equal to this, and then we take product of these three matrices and you get this result. So, you get these two expressions for the inverse of A, B, C, D. One expression you get here, and another expression you get here. So, obviously, from here you obtain A minus B D inverse C inverse is equal to this matrix. So, we get this kind of results. So, suppose A, B, C, D, these are matrices of suitable order and A and C are non-singular, then A plus B C D inverse is equal to A inverse minus A inverse B plus into C inverse plus D A inverse B whole inverse D A inverse. And similarly, you get this result. You have to obtain the inverse of matrix A, B, C, D or A minus B, D, C using those two procedures, and then you just equate the matrices, corresponding matrices, then you get these results. So, you calculate an inverse in terms of A inverse B, C, D, and then you calculate an inverse in terms of A, B, C inverse and D, and then equate top left block of inverse matrices to obtain these two results. Now, we define quadratic form. So, suppose A is n cross n matrix with ijth element A I j. So, A is a square matrix and X is n cross 1 vector x 1, x 2, x n transpose. Then you can easily obtain X transpose A x, which is equal to summation I equal to 1 to n, summation j equal to 1 to n, A I j x I x j. So, this is actually a quadratic form. Now, if this quadratic form X transpose A x is greater than 0 for all non-null x, means for all x not equal to 0, then we say that A is the matrix A is positive definite. If X transpose A x is greater than or equal to 0 for all non-null x, then we say that the matrix A is positive semi-definite. If X transpose A x is less than 0 for all non-null x, then we say that A is negative definite. Similarly, you may define negative semi-definite matrix. Now, suppose lambda 1, lambda 2, lambda n, these are the eigenvalues of an n cross n positive definite matrix A. Then lambda I is greater than 0 for all I, means the eigenvalues of a positive definite matrix are always greater than 0. To prove this result, suppose P I is the eigenvector corresponding to lambda I, then such that P I transpose P I is equal to 1 for all I. Then A P I is equal to lambda I P I. Then we pre-multiply both sides by P I transpose. So, P I transpose A P I is equal to lambda I P I transpose P I, and P I transpose P I is equal to 1. So, finally, you obtain lambda I. And since this is a quadratic form, P I transpose A P I is a quadratic form and A is positive definite. So, this quadratic form is always greater than 0, and this leads to the result that lambda I is greater than 0 for all I. So, in this lecture, we have discussed different basic definitions and the results of matrix algebra, which we may require in subsequent lectures. Actually, the nature of different econometric models is multivariate, and for deriving the expressions for different estimators or for studying the properties of different estimators, it becomes more convenient if we use the matrix notations or if we use different matrix results. So, that is why in this lecture I have briefly discussed all these results, though I have not gone into the details of derivations. If you are interested in details of derivations of all these results, then you may consult some good matrix algebra book. So, here I am going to stop. Thank you very much.